What do we have here? Oh man. Okay. I just did this about half an hour ago with the previous class. Um, let me send you a very quick one for that. Okay, I just did this only. It's fine. I mean, the previous class was the IB class, but they're the same. Hang on, I'm trying to do this while I'm eating, so let me just. I do things a bit slowly, sorry, I know. Uh, Wait, sorry, I'm trying to do this while I'm eating. That's not good. That's not a good idea. What? 30:89. Yeah, it's actually an 8-minute thing only. Okay, I sent you that. Do you understand why the kinetic energy is different? Right? Because the antinode, basically, for the same period, right? The antinode needs to travel a bigger distance than any other particle. Right? Because antinode need to go all the way up and all the way down. But the non-antinode particles, like particle A is a non-antinode particle. He only needs to go up and down like that distance, but in the same period as B. So in terms of kinetic energy, the maximum Ke, when they're passing through equilibrium, B will be more than A. This one is correct. Because when it's passing through the equilibrium, B is faster. B has to travel a longer distance in the same period of time. So that itself means that it's faster. Right? You see B has to travel a longer distance, right? Then A, right? In the same period, A makes one oscillation, B makes one oscillation, but B overall has a greater speed. So the maximum Ke of B is greater. Okay? If you look around the video that I sent you, I think you can also see me talking a bit about like the speed and all that. Right? So feel free to just look around it. It's fine one. It's just that since I have a recording for that concept, I send it to you so that this session will not take so long. Right? And after I drop the call already, I can go and do my thing. Yeah. Okay, wait. So I'm still trying to eat my yeah, okay. Almost done. Okay. So right, I continue. I round robin now. I do Yuhin's question. Yuhin, you have sent me some questions from long time ago. Long time ago, so sorry, so long ago. Oh man. Okay, okay. Is it this one? Okay, this one, So 20, right? Okay, wait, I haven't even read the question yet. Wave generated from X and Y produce water waves that meet at point Z. Okay, X travel to Z, Y travel to Z. Okay, same wavelength, point Z, same amplitude as that from Y. Distances XZ, YZ are shown 24 cm, 34 cm. When the wave generators are in phase, amplitude at Z is 0. This means destructive interference. This means the phase difference is pi radians. This means that the path difference is n plus half wavelengths. Like n can be an integer. Okay? This means that n can be 0, can be 1, can be 2, can be 3, as long as you end up with like half a wavelength. So 10 cm equals to n plus half lambda. Your job is to find a wavelength that you can fit into that equation where n is an integer value. Shoots. Oh, yes. That means 10 divided by 2, 10 divided by 3, 10 divided by 4, 10 divided by 6. Let's move it all up. So do you understand that it's kind of like 10 over lambda is equals to n plus half? Then your job is to check which one will give you a whole number. Like which of those values there will give you a whole number. Let's say you 10 divided by 2 is what? It's 5, right? 5 equals to n plus half. N is not a whole number. I think the only answer is 10 divided by 4 only. Like C is your answer. Oh yeah, C is the answer. So 10 divided by 4 gives you how many? 2.5 wavelengths, right? So that means the n is 2, so that will give you a destructive interference. Yeah, there you go. Yeah, so I think what you're missing, I see you're working. What you're missing is this thing here. So for destructive interference, the path difference is n plus half lambda, and n is integer value, 0, 1, 2, 3, 4, 5. Okay, back to Huijin. Hang on. It's another image, right, Huijin? Okay, no, because sometimes that you may take a picture and then you may have more than one question. Okay, what's your question here? What the? Okay, so is it me or your superposition a bit shaky? Right? Your superposition a bit shaky, But I thought I got go through superposition with you. Oh, okay. Okay. So the thing is, identical sources. What's in the middle here? Okay. The n equals to what there? Mm-hmm. Then how about this one? Okay. What does a 1 represent? Other than that? Don't know, is it? Okay. The 1 represents one wavelength. Okay, let's say I choose one point there, right? Is there a constructive interference there? So I draw one line from one source, pointing to that point, and I draw another line to another source, pointing to the same point there. So these two have diffracted waves, so the waves are traveling over there, and then they meet there, they have constructive interference. But how many wavelengths apart are they? Like, you can see that this line, right, the first blue line I drew, is a bit shorter than the second blue line. How much shorter? One wavelength. Ah. What's the label for this one? So if I were to draw one line from this source to, let's say, a point here like this, and I draw another line from the other source to the point there like that, one is shorter than the other. How much shorter? Two wavelengths. So the order is also representing the path difference. That's what you're missing at. That's why you couldn't do this one. Okay? So if they want you to find path difference of 1.5 lambda, you're finding n equals to 1.5. Okay? Now, you know the answer already, but I can prescribe you a video to understand this more in depth. So I'm going to prescribe it to you because I scared you don't get the full picture. You understand what I'm saying? Yeah, I'm prescribed to you first. Let me type it out for you. Okay? Okay. Settle already this one? Then I go through Yihin ones. Yeah. Yihin actually have a lot of backlog first. No, I got a lot of backlog for your question because I think for the last week of June I was just very busy with my kids. My own kids are. So that's why I couldn't. Whoa. Oh, okay. So they're saying that two source falls on the screen and they tell you that the light intensity is 0. So at first point, on the first idea, this is what? Destructive interference, right? Yeah, so it's destructive, right? So light intensity is 0. Why are you circling the weirdest things? I'll circle 0. So this is the dark fringe. This is a destructive interference, DI. Okay? Okay. Is P at the midpoint? I'm sorry, I can't tell. Is it meant to be directly at the midpoint? No, right? Okay. Okay. Because, right, if P is directly at the midpoint, if P is directly at the midpoint, and if it's a dark fringe, right, then there's something wrong with the sources. So let me just go through this very quickly with you. Let me ask you a couple of leading questions. Okay, R, S, P right at the midpoint. So this one here, I tell you that P is directly at the midpoint here. Okay, see the diagram I drew for you already? Okay, directly at the midpoint is right smack in the middle. But it's a dark fringe. How is that possible? How is it possible that I have two sources, okay, and they're interfering, and then right in the middle is a dark fringe? Because by right, what is it supposed to be? It's supposed to be central maxima, right? Yeah, but then it turns out to be a dark fringe. So why is that? How can that even happen, or why is that possible? Okay, so that is possible when R and S are out of phase. That means the source themselves is out of phase. That means R and S, right? They are playing anti-phase to each other, right? So sometimes I like to use tapping as an example. So R and S, right? They're out of phase, so they're making sounds that sounds like this, right? Out of phase. So when the waves travel the same distance, when one of it is a positive amplitude, the other one is a negative amplitude. So it will meet here and then they'll do disrupting interference. So there's a chance that the sources could be out of phase. So if you look at the options of your worksheet, right? This one here, okay, it gives you a few possibilities. But light from the two sources is emitted out of phase. Light from the two sources is emitted in phase. Light from the two sources emitted 90 degrees out of phase. Right? Part C to me sounds a bit weird. Right? I mean, option C sounds a bit weird because it is going to be very hard to determine whether a source is going to do constructive or destructive when it's 90 degrees out of phase. If anything, I will strike out C first. I won't take C as answer first. Okay? Then I look at the last one, light from the two sources in phase. Oh yo. Okay. So you got to remember this trick, okay? Two wrongs make a right. Two wrongs make a right. Do you understand that phrase? Okay. Two wrongs make a right, huh? So let me just show you this. Okay, come back here like this. Let's say we are still talking about this. This is out of phase. Okay. Let's say immediately to the side here, right? You see where my red dot is, right? Okay. Right. Let's say I tell you that that's a bright fringe. Right, that's a bright point. Can you explain why is it bright? So they happen to be in phase, right? But then they're out of phase from the start. So how do they become in phase there? Yeah, correct. It's because of the path difference, right? So one side is shorter than the other, right? How much? Half a wavelength. Okay. So this is an application of the standard thing. So I have to backtrack a bit. Okay, P, Q, and T, for example. Okay, I give you a backtrack a bit. Okay, so this one, let's say this one are in phase. Both P and Q are in phase. Okay, right? I have two sources, they are in phase. Can? Okay, then they meet in the middle, right? Is the path the same? Is there any path difference? No path difference. So n equals to 0, right? Di. Sorry, Ci. Right? Constructing interference, central max, right? Central max. But what happens if how about the next one? Let's say another one here. Okay, this is n equals to 1. Based on Hui Jun's question just now, I really went through it. So the 1 represents what? So which means that one side is shorter, the other side is longer. The difference of the two paths is one wavelength, right? Okay, they are in phase, and then the path difference is one wavelength. So this here will end up being what? Constructive interference also, right? Okay, so then what happens here in the middle? is destructive, right? Interference, right? What's the n value? 0.5. So 0.5 represents what? Correct. So they are in phase, but then because of the path is 0.5, they end up being out of phase. Okay, now back to this one. This one here, from the beginning, the two sources are already out of phase. They control it like that. They already made it out of phase. So even though they meet in the middle, right here, path difference is 0. The same distance, and they reach point P, it ends up being a dark fringe because they happen to be out of phase. So like this is like the reverse of that happening. So the question is, if I have a bright fringe, right next to the dark fringe, the one in the middle, right, is a bright fringe. How do you make it bright? So they're out of phase, and if they're one wavelength apart, right, they will continue to be out of phase here. So it wouldn't be bright here. So the question is, how does it become bright? It becomes bright because the path difference is 0.5 wavelengths. So the idea here is two wrongs make a right. So they're out of phase, and then the path difference make them out of phase again. So out of phase become in phase. Because when you're out of phase, you shift by half a wavelength. Then when the path difference is half a wavelength, you end up being in phase again. So therefore, it's a bright fringe. So a bright fringe is like, right, there's something wrong at the source, there's something wrong with the path, they kind of like net off each other, it becomes a bright fringe. Two wrongs make a right. Okay, wait, back to the question here. So the question here is asking you, at point P, at some random point, it's not in the middle, is a destructive interference, okay? So you have to choose, okay? So they are suggesting that they are out of phase, okay? They're out of phase, and the path difference is half lambda. Now that would mean that if it's out of phase, this is wrong, right? This is out of phase, right? That's like a wrong, right? And then the path difference is half wavelength. That's also another wrong, right? So you got one wrong, you got another wrong. Then option A will tell us that it will become a bright fringe, not a dark fringe, correct? They are looking for a dark fringe. So then we have to check. A cannot really. Light from the two sources, in phase, that's a right. And the path difference is lambda, that's also another right. Then it should have been bright fringe also, B. Then we look at the last one. Two sources is emitted in phase and the path difference is half lambda. D is the answer. Because that's the only option in this whole thing that can give you a dark fringe. But I think a bit silly lah. They should have given an option. I mean, the answer, I feel lah, if you want to set this kind of question, right, then I think your answer should be this. The two sources is out of phase by 180 degrees and the path difference is lambda. Right? Yeah, then I think that will be more worth your time understanding all that lah. But you know, whatever I explain is to explain why A is wrong. Yeah. Okay. Now Hui Jun's turn. Hang on. Now Hui Jun's turn. Hui Jun. This one is. Wow, I just did this in standing waves. Fuyo, ayo, okay. Okay. Regina, this question not exactly very fair. Okay. Because I think maybe because partly because the teacher never said the question correctly lah, right? So did you assume that there was a standing wave inside? Yeah lah. I mean, it's not explicitly stated lah that there's a standing wave. You could very well have been looking at just a normal sound wave that's traveling through the pipe. Yeah, right. It's kind of annoying. Okay. But yes, okay, fine. There's a standing wave inside. Uh, the options here are all very varied. Yeah. But we can see what compression, rarefaction, right? Hmm. Do you know that for standing waves, compression, rarefactions are the nodes? Looks like you do. Yeah, they are the nodes, right? Okay. And then the open end there is a antinode. Okay, so looks like you do. So I guess you are correct. So this is a node, this is a node, this is a node, this is a node, and I mean that's gonna be a node as well. So your yeah. Something like that? Yeah. Okay. Which one is not correct? There's more than two complete wavelengths in the tube. That is correct, right? Yeah. Uh, air pressure variation is maximum, but air velocity is zero at the end because this is a node, right? So air velocity is zero. That's correct. Air pressure is maximum here. This is a compression, right? Because at the node, the particle not moving, ma. Yeah, yeah, right. So I would take A as the correct answer statement also. But you also take D what? Oh you thought A was the answer. Yeah, yeah. A is not the answer. So you also understand that D is correct, right? 9 times. Can you tell that this is the ninth harmonic? How do you tell that this is a ninth harmonic? 9 quarters. Okay, so there's 9 quarters, right? Mm-hmm. Correct. The graph is a straight line. So the idea here is yeah, lah, the graph is a straight line. Yeah, the graph is a straight line like this. So that means the graph will straighten out like that. What that means also is all the particles will be kind of like all like spread out evenly, like for that one very moment. Have you seen the GIF I showed you before? Yeah, you know the GIF, right? The particles moving one, okay? So it's a straight line. Oh, hang on, they're asking for open end, right? Open end. This is an antinode, right? So, oh, if it's an antinode, yeah, at the t equals to 4, at the t equals to period over 4, the antinode particle is back at equilibrium. So it is, no, it's moving with the greatest speed. Eh? Yeah, you're right, C is wrong, You mean you mark already the C is the answer, is it? Wait, at the instant of t equals to 4, t over 4, that means 1/4 of a period, right? The antinode particle, no, there's no such thing as a antinode becoming a node. Like a node is a node only. At 1/4 period, the graph is flat, which means all particles are passing through their equilibriums, right? All particles are passing through their equilibriums. All particles are passing through their equilibriums, which means that the particles all have their maximum speed, right? They are at the maximum speed. Sorry. Ah, ah. Okay, I need to check. NJC 2016, is it? Paper what? How come we got two? Oh yeah, sorry. MCQ paper one. Paper one question what? No, they didn't say. Yeah, this one. So 21. Question 21. I look for the answer key. 21 answer is C here. 21 answer is C, huh? Right. Yeah, let me just double check again. 21. I think got something wrong. Yeah. No, no, no. Okay, okay. I think it's better if I show it to you on a GIF. Because if I keep describing to you, right, it's very hard to describe to you using words. Let me just show you the thing first. So I can't pause this thing, but maybe I can take a screenshot. I'll see. I'll see whether I can do that. But basically, the particles at the open end, right? This is the open end. It has the biggest amplitude, right? Up, down, up, down, up, down, like that, right? Okay. So the idea is the kind of like the picture that they give us is when this guy is a compression, right? Like next to the open end is a compression here, right? Right. Then they pause the picture and then they send it to us, right? Right. So maybe I'll try to do that. Maybe I'll try to do that. Okay, 1, 2, 3. Shit. You know. 1, 2, 3. Okay, solid. Okay, so I screenshot this one. So let's discuss. Let's kind of like figure out what's going on here. So right now, the wave shape is like that, right? At this moment, right, when the graph is like this, at this very moment, right, nothing is moving. Every particle is at its respective amplitude. Like this is at its amplitude, this one is at the amplitude. They're basically all at their maximum displacements, right? So when you have a particle at the maximum displacement, it is at rest, right? So for a very short instant of time, nothing is moving in this picture, right? If the graph looks like this, okay? But when the graph is flat, wait, oops, oops, shoot, can't catch the thing. Ah, okay, I got it. Yeah, yeah. This displacement versus the positions of the graph. Yeah, that's right. So you see, right, when you have this graph like that, okay, all your particles are at a oh, not only just the nodes, every particle is all at their amplitudes and basically they're all not moving at that very moment. Okay? And when the graph looks like this, you get compressions and refractions, compressions and refractions. But when the graph is like this, whoop, like that, right? One flat line like that, that's like, isn't that t over 4? That's like 1/4 of a period from here to here, right? That's when the graph is flat, right? Look at all the particles. Yeah, it's spread out, no compression, no refraction, right? But then the question is saying that at the open end, at this period of time, so where's the particle? The particle is actually is passing through its equilibrium, correct? Okay, so there's a danger of saying that, oh, the particles are at equilibrium. Do you know what it sounds like when I say that? Oh, all the particles are equilibrium because the graph is equilibrium, right? Do you know what's the danger of saying that the particles are equilibrium? Because then you start to think that, oh, they are not all not moving. When you have a pendulum, right? SHM, when is the particle moving the fastest? When it's passing through the equilibrium. So when the graph is flat like that, right, it's actually passing through the equilibrium at the greatest speed. So that's why I say that there's something wrong with the options. I do believe that the answer here is wrong, right? Something is wrong. The air pressure variation is zero. Yes, that's correct. Okay, that's correct. But then the air acceleration should not be maximum because for acceleration to be a maximum, right, for the particle to be at maximum acceleration, it needs to be at its amplitude because it's like SHM, right? Greatest amplitude, greatest acceleration, right? Velocity is zero. Again, think of a pendulum. When your pendulum is at its amplitude, what's the speed? Zero. What's the displacement? Maximum. What's the acceleration? Also maximum. Zero speed, but maximum acceleration. Then when the pendulum is passing through the equilibrium, maximum speed, zero displacement, zero acceleration. Just think of a pendulum going back and forth, like swinging back and forth like that. Correct, right? Okay, so I don't know why the option is saying that the acceleration is maximum. Oh shit! Yes. Okay. Yeah. Yeah. Okay. Okay. Yeah. Then that's why this is wrong because at the open end, the acceleration is supposed to be zero when t equals to t period over 4. Yes. Sorry. Yeah. So C is the answer because like at t equals to 4, the graph is straight. All the particles except the nodes have its greatest velocity, their respective greatest velocity, right? So it's like, you see, when the graph is at the amplitude, right, the particles stop for a moment. You see, let me just try to see, stop, stop. That is right. It stops for a moment because it's changing direction. Yeah. Okay. Sorry. Took a bit too long for that one because I thought I was getting it wrong. What? Sorry. Okay, we are now Yu Hin's turn. Hang on. This coherent sources. Oh, okay. So two coherent sources. Ugh, the color is very off. S1, S2, traveling overhead, traveling at speed v, altitude h, detects. Is this R? What? Oh, F. Where did it go? F, maxima of intensity per unit time. So frequency lah, right? Okay, that's fine. Okay. So this is again two source interference. So kind of like, are you having trouble with two source interference? One source here, right? And then basically what do they create? They create maxima, right? Maxima, 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 right? I mean, what's in between the two maximas? A minima, but they didn't bother about minima because they said it detects maxima. Okay? So as your satellite is flying across, phew, it's experiencing a certain number of maximas per unit time. Okay? So at the same time, we should understand that the distance between the two maxima should be approximately the same. Sorry, the symbol that we use is x, right? X. Okay? So in a way, V equals to x over t. Right? V equals x over t. V equals to x over t. V equals to fx. Correct or not? It's so random. It's like out of nowhere one. Because the what the time taken from one x to another, right? Time taken from one x to another. Let's say I take it as the period lah, right? The period between two maximas, right? Between two maximas. Then I can do f equals to 1 over t, right? And then I get fx. So the speed of the satellite is frequency of the maximas multiplied by the distance between the maximas. Right? That's the link. I don't know whether that will help, but I'll just leave it there first. Okay? Huh? So, oh, whoa, 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 okay. I'm getting a bit confused already. Okay, this is the part where I'm not too sure what you're asking. Okay, no, this speed is a satellite speed. It's not a wave speed, right? It's the satellite speed. The satellite is traveling across. Yeah, yeah. So the v is related to the x, right? So the x is the distance traveled by the satellite and the time taken by the satellite to go from one maxima to another maxima. Okay. So the idea here is that this is approximated to two-slit interference. So what's the equation for two-slit interference? Lambda. Lambda. Okay, lambda d over a, is it? Okay, okay, so I write this down first. This is original, huh? So x is equal to lambda h over small d. H will be the distance from the sources to the screen, and then small d is the separation of the sources. Like that. Okay? What do they want you to find? Wavelength, right? You try to sub this into this and make wavelength the subject. Yeah, that's the annoying part about this question. Can yeah. So I think the tough part was the difficult part of this is to convert the 1 over t into frequency. I think that's the part where most students will not be able to catch. Then I go through another one of Hui Chin's one, round robin. Oh, what's this? Where's this from? 2015 A levels, okay? Yeah, I'm trying to recall this question also. This was one. Explain why the G field strength at the position of each moon has the same magnitude and direction as the centripetal acceleration of the moon. Okay, okay. Wait, this is Jupiter, right? This is Jupiter. Okay. Then this one is the moon. Talking to the moon. Right. So that's the moon over there, right? I mean, I don't care what the name is, lah, right? They're basically asking you why the G field strength at the position of each moon. Right. Let's understand this statement first. G field strength at the position of each moon. Right. Okay. Do you understand that they are not asking you about the G field strength of the moon? They are saying the G field strength that the moon experiences. Okay, can I? Okay, so I'm going to erase the moon. Okay, because they're asking you at the position of the moon. So I erase the moon, right? I got rid of the moon, but now I replace it with a cross because I would just want to talk about like the position of where the moon is, lah, right? So the G field strength at the position of the moon, the G field strength is due to what? And where is it pointing? Okay, so this is G of Jupiter at this position. You understand this? Okay, they are asking you why is this G equal to the centripetal acceleration that the moon experiences. So let's bring back the moon again. So we know that the moon orbits around Jupiter, right? Okay. So let's say I just draw it slightly to the side here like this, right? This is the moon, huh? Okay. So does the moon experience centripetal acceleration? How you know? Okay. So you're saying that you also agree that there is a centripetal acceleration. Okay. So the question is just asking you, why is this G the same as this AC? Right? You understand the question now? Okay. So how do we answer this? So we answer this by just saying, right, that the gravitational force that the moon experiences due to Jupiter provides for the centripetal force that the moon uses to orbit. I don't know how you explain it. What was this? I guess you can actually, like nowadays I hear a lot of the students tell me that the teachers say that you can actually just show the equation and explain. So there's nothing wrong with what you're doing here. So what you did was you just say the centripetal force MAC equals to GMM over R squared, and then AC equals to GM over R squared, and therefore the centripetal force is equals to the G field strength. Then the answer is yeah, can. Yeah, I think this is okay. Yeah. But I think if in case of phrasing, right, I will always encourage students to rephrase it and say that, okay, the gravitational force that Jupiter acts on the moon provides for the centripetal force, right, that the moon uses to orbit around Jupiter, right? Then I will write the equation down. I mean, I was just about to write the equation down, right? Therefore, GMM over R squared equals to MAC, yeah, MAC, correct. And then therefore, GM over R squared equals AC, right? G field strength is the centripetal acceleration, okay? Then you need to address the direction, right? Because I think you mentioned this, you didn't mention the direction, right? Okay, then you have to say that the gravitational force points towards the center of Jupiter, which happens to be the center of the moon's orbit. The center of Jupiter, which happens to be the center of the moon's orbit. That's why they're pointing in the same direction. That's why the G field strength and the centripetal acceleration are pointing in the same direction. Okay. Okay. So unfortunately, yeah, you understand the concept now, but you will realize that the answer key, now remember, the answer key did mention something like this: very much greater than the mass of Io and yeah, this one here. Okay, this is very frustrating because what the answer key is suggesting is that, oh, actually the question seems like it's asking you why is the acceleration of a moon, of one of the moons, not affected by the presence of another moon? Because the idea here is this: if you have two objects, two bodies, right, Jupiter and moon, everything is okay. But then when you have three body problem, right, when you have a three body problem, right, then how about the attraction by this moon, right, on that moon? You know, wouldn't that change the direction of the resultant force? So it's a very annoying question, right? And to be honest, like, I mean, now that I think back about it, like, this is me trying to explain to you how to interpret this. Okay, they essentially are asking how come the moons don't affect the orbits, and the answer is because the Jupiter's mass is much greater than any of the individual moons. So the resultant force on the moons, right, the gravitational force acting on the moons, right, by Jupiter, right, is much bigger than the gravitational force between the two of them, which is negligible. Yeah. So therefore, the force, the field strength by Jupiter is solely, it can be assumed that, or rather it can be approximated that it is the only acceleration that the moon experiences and not due to any other bodies. Okay, let me tell you this. So this is an annoying question, right? I know, I understand it's annoying, but it happens once out of, like, you know, 1 out of like 20 marks that you do. Like 1 out of maybe every other 15 to 20 marks, you'll get one annoying question like this, right? I'll tell you this, if I were to sit in for the exam, I would have written down my original answer. I would have also kind of like missed this point. I probably would have lost 1 mark. Okay, 1 mark, not big a deal, let go, right? Okay, in the exam, you wouldn't know, right? You wouldn't know, you wouldn't go and be like, walao, what, like, you know, you wouldn't be thinking of like wasting time on it, right? You would have written this and this would have been the answer. Okay, I'm gonna tell you this, okay, you're gonna get 1 mark, not 2. Okay, which is fine, but if you can hit more questions, like you can hit most of the other questions, like 80% of the questions, you are safe. Okay, but you won't know one. This one is very hard to know one. This one is only if I look at the answer key, then I realize, oh yeah, shit, that's what they're asking for. They're asking you to. But you see, right, that's the problem with A-level questions. Sometimes they're not clear. They're very vague one, right? If you want to ask me whether the moons affect each other, why don't you just ask me directly? Why don't you just say that? Explain why the moons don't exert a gravitational, or rather, explain why the moons gravitational force on each other is not considered or can be considered negligible. Then the answer would have been, I would have known the answer would have been the Jupiter's mass is much bigger. Okay, but now you're gonna ask me, am I supposed to know roughly what's the solar system like? Right? Because how am I supposed to know that Jupiter was like hugely massive? Right? That's another question. So my answer to you is you sort of have to know. You have to know how, like, you don't have to know numerically, but you need to know like the sun is the biggest thing in the solar system. Jupiter is second biggest. Yeah. Then you have to sort of like know the order of the planets and all that as well. Okay? Now, if there's not enough time for you to go and figure that out in before your prelims, of course, don't go and waste time doing that. That's fine. Just leave it alone. But just understand that we've got like 8 planets, and each planet has their moons, right? Earth has moon. Mars has 2 moons. Jupiter has 69 moons. But you don't have to know the number. Sorry. Just understand that planets have their own moons. Yeah. But if you don't have time to go and figure that out by tomorrow, don't worry. Just let it go for now. Can? Yeah. Yeah. Then back to Yushin. Hang on. Oh yeah lah, of course, yes, you're right. Yeah, yeah. But if let's say the question trying to suggest that, how come the moon like not affected by the sun, even though the sun is very big, then your answer is the moon is very small and is very far away from the sun, and it's closer to Jupiter. Yeah, something like that lah. Yeah. Sometimes the question is have to be answered in a politically correct way. Yeah. That means you, yeah. Okay, what was this about? Hang on, So 97.14 equals to GM over R plus 600. 89.73 equals to GM R plus 2300. And you understand already, right? Because it's the entire distance. Like you have to take it from here. What do you do? I also don't know why you put 3000. Just always remember that you must measure from the surface all the way to the center of the Earth. Right, so center of the object. So this is R plus 600, and then the other one is R plus 600 plus 1700. Yeah. Hang on, let me just do your another one of yours. Because I think I got quite a little bit of backlog for her question. Okay, Huijin, I do you use one more. You hint, sorry, not you hint. Only part 3 is the problem, is it? Part 3 lah. Part 4 you got correct. Okay. SHM, right? Always think of it as pendulum. Okay. So you see pendulum, swing down, swing up, swing down, swing up. Okay, not? Wait, Let me draw more positions for you. So you could be going down this way, you could be going up this way, and you could be going down this way, you could be going up this way. Okay, so this is the tough part because there's so many variations of this. Okay, like at this position A. Okay, what's the acceleration? Maximum and pointing. Okay, what's the displacement? Uh-huh. Yeah, pointing to the left, correct. Velocity is 0, correct? Okay, then B. B is when it's going downwards like this. Where's the acceleration for B? So acceleration pointing to the right, but it's not maximum. How about the displacement? Also pointing to the left, but not maximum. How about the V? V is pointing towards the right. In the middle, V max pointing towards the right. A0, X0. Okay, then when it's swinging up, right? So this is this in the middle of position C. So position D. So V is pointing to the right. Acceleration is pointing to the left. Displacement is pointing to the right. Correct? Then at the very end here, so this is E. This will be V equals to 0. A naught is pointing towards the left. X naught is pointing towards the right. But then you got to let it swing back because I want to find the whole range. So the next one is F here. All right, so when it's at F and it's going down, the V is pointing towards the right. Sorry, left. Correct or not? The V is pointing towards the left. The X is pointing towards the right. And the A is pointing towards the left. Okay, then it will be here, then V naught pointing to the left, right? A equals to 0, X equals to 0. Then there's this G, then H, position H. So position H is when this thing is going upwards like this, okay? So the displacement is to the left, the velocity is to the left, okay? And the acceleration is pointing towards the right. Then at the very end, right, it resets to A again. So my point of doing this is to show you that at some positions, right, at some positions, you actually do have displacement and velocity pointing in the same direction. Like this, okay? Or even here like this when it's pointing like that. Then sometimes your velocity and displacement are pointing opposite directions, like maybe this one here for B, right? X is pointing to the left, V is pointing towards the right. Okay? So trying to show you that like could we have acceleration and velocity pointing in the same direction? Yeah, can. Like for example, B, velocity, acceleration pointing in the same direction. For example, F, right? Velocity, acceleration pointing in the same direction. Okay, so that could be the case. But then of course that doesn't help you in this sense because that's a pendulum and this one is a wave, right? But I mean, I'm just trying to show you the pendulum first. Okay, then what happens is, right, I need to show you how to do it on the wave. Right, the particles are all there. Right, the particles are all here like this. On the wave like that, huh? Okay, so is the wave traveling somewhere? Where's the wave traveling to? Okay, so we draw a shaded wave, right? I mean, we draw a shifted wave. We draw a shifted wave like that. So something like that. Okay, then what you can do also again is this, right? So for the particles at the bottom, right? For these particles here, where are they going next? Upwards. Okay, so they have negative displacement but positive velocity. Their displacement is below the equilibrium line, but their velocity is going upwards. They're headed upwards. Well, why would you use the word increasing? Sorry. Okay, so what we are trying to figure out is the direction. We are not trying to figure out what's the, like, whether it's increasing or not at this time. So one more time, the displacement now, is it negative? Okay, then after this picture, right after the black color picture, right, the particles will move into the blue line, right? So their direction of motion now is actually upwards. Yeah. So displacement is negative, but velocity is positive because velocity is pointing upwards. Then for this whole section here, do you see this whole section here? This one here, my finger is pointing there. What are all the particles going to do? They're going to start moving downwards. Okay, but here's the thing. What's the displacement of these ones here? Negative displacement, and their velocity is also pointing downwards. So if you select any particles from here, that will help you answer part 3. Velocity is in the same direction as the displacement. How about these ones here? So these particles are moving downwards, but what kind of displacement do they have now? So you have positive displacements but negative velocity. So that's not the one there, right? Okay. Then how about this ones here? And their velocity is, yes, positive also. So positive displacement and positive velocity. But how about this one down here? Correct. So I think one thing I do see the corrections. I do see your corrections. Okay. But I think you need to recognize that these, for the answer, right? For the answer here, these particles is what you're looking for, right? Because they have the same direction and of displacement and velocity. No, this one's here. Yeah, this one's here have the same direction of displacement and velocity. Negative displacement and negative velocity, currently negative velocity. And then the other one you're looking for is here. This one here. This section here. Yeah, this section here. Yeah. Then you do the same thing, right? Acceleration is the same as velocity. Acceleration is the same as velocity. See, acceleration is always pointing towards equilibrium. Acceleration is always pointing towards equilibrium. So if you look at any particles, if the velocity happens to be like about to hit the equilibrium, then those particles have the same acceleration and velocity direction. Yeah, so I think like A, and I think B also. Now B, right? B happens to be crossing the equilibrium, right? Don't forget, B right now the displacement is 0, right? Don't forget about that. But technically speaking, it's not very fair because actually B is supposed to have 0 acceleration also. Yeah, B is supposed to have 0 acceleration. So technically B is not correct answer. Correct or not? But because this is a school tutorial question, it's meant for discussion. It's not really kind of like an exam type of question. So, I guess in a way you be reassured that they're not gonna ask this because this is not a good question. Because for B, right, the acceleration is 0. So what is the acceleration? Don't have acceleration. Yeah. Then B is maximum velocity now, right? Passing through the equilibrium. So B is not. I wouldn't take B as an answer. D. Now D. So D is on the other flip side. D is where now? D is at its amplitude now, right? Now, right? Okay. So D's velocity now is 0. Like for this instant now is 0. Okay. So D also cannot because D the velocity is supposed to be 0. Okay, unless I modify the question and I say this, in a short while after this picture, in a short while after this picture, okay, then where will the acceleration and velocity be the same? Then the answer will be A, B, and D. Yeah, no, sorry, A and D only. In a short while after this picture, A and D is the correct answer because B, right? B will, after it moves down, right? After it moves slightly down a bit, because it's on its way down, right? After it moves slightly down, the acceleration will point upwards towards the equilibrium already. Right? Then the velocity is pointing down. So B shouldn't be. I mean, the closest answer actually, I think which is right. The closest answer should be D. Right? Because immediately after this picture, if this is t equals to 0 and t equals to 0.101, right, for example, D will be the answer here already. Yeah. Okay, let's go to Huijin now. Okay, what's this? Oh, I think you understand the increase in speed, but I think you just forgot that in electric field, charged particle is always a parabolic path, not circular. Yeah, lah, yeah. I mean, it's not. You cannot call it radius because it's parabolic, right? Okay, decreased radius of circular arc literally means more deflection also. Like if your circle is like that versus your circle is like this, right? The smaller circle means greater deflection. So you're not wrong to think that the path will become more curved. Correct. Yeah, yeah. Okay. Wait, then if that's the case, you actually only got one more only, right? Let me just settle your one first, then I go back to 18, okay? Because this one here was a fast one. Okay, so this is a very annoying question. Okay, I think the question here is basically we don't know what's the length of this wire. Do you want me to find the resistance, right? R equals to rho L over A, right? You got the L and you have a diameter, so you can find the A, right? Right. So the A is the cross sectional wire, cross section of the wire here. Like this. Like this is the A, right? If let's say I pull out the wire like that a little bit, right? That's the A there, the construction area, right? Okay, so the only thing that you have no idea is L. Like what's the total length of the wire? Correct? Because the current needs to flow through the entire length, right? Correct, or is the circumference of the cylinder, right? Then you multiply by 30 times. Yeah, the rod is the holder lah. The rod is the holder. So actually, you're just trying to find 30 times of the circumference. That will be the length of the wire. Yeah, silly question though, actually. This one, they're being annoying. Okay, let's continue with Yi question. Oh boy, I think I've got quite a few coming from her side. Hang on, Okay, what's this about? Is Oh gosh. Okay, is it a legit question? Like is it a legit exam question or is it just a school thing? Feels like it's a school thing though, actually. Which what, sorry? I guess they won't test it in like they'll probably break it up into a few parts. This is more like a paper two question. They'll break it up in a few parts and they'll ask you separately. But yeah, I mean generally I can sort of tell that you are doing it correctly. But yeah, okay, that's fine. I mean I'll just go through it anyway. So the idea here is that one to find the phase difference between 2 points, let's say P and Q, right? You essentially they have to depend on a few things like it could be what's the distance, what's the linear distance between P and Q, and then you divide it by the wavelength. So if let's say you take del path and you divide it by the wavelength, that will be phase difference, right? And you multiply by two pi lah, right? 2 pi radians, right? Then you'll get, you know, then you get the phase difference. Okay, but in this particular case, I think the axis is a time axis. So we talk about time difference, like what's the time difference between the two, which is what you have shown in the working here. And if you take it, divide it by the entire period, and you times 2 pi, then that will be the phase difference, right? So the question is, how do you find the difference of the two, right? What's the difference, right? Right. So like, what's the time taken? So to do that, you need to do x equals to x naught, right? Sine omega t. So your question here is actually, how do I use this equation, right? So if let's say you try to apply you try to apply it, okay, you try to apply it, you basically would have found, like, let's say you sub it in, minus 0.5 y naught, right, equals to y naught sine omega t, right? Correct? Do you understand what I'm doing down here? Okay. Then when you calculate, right, you got a certain t, is it? Do you get a t somewhere? Where do you get? Huh? What? Oh, so just t over 12, is it? I mean, don't go and leave the minus sign inside lah, right? Yeah. Why is there a minus sign? No leh. It doesn't make sense, eh? Oh no, because okay, no, because if okay, so the thing is that if you're using sine, if you're using sine, okay, and then we're trying to find the time taken for particle Q, right? Okay, to go from equilibrium downwards, right? Then that is a negative sign graph. That means you're taking Q to be behaving like this, like it goes down. So there's a negative sign graph. Is a negative sign graph on this side. So you leave the negative sign there, and then the negative sign will both sides will cancel off. Okay, so anyway, t equals to 12, right? Okay, here's the problem. Okay, you look at this number, t equals to t over 12. When you do this trigo calculation, when you did that trigo calculation, you went to find this displacement, right? This displacement, right? And let's say we use negative sign, the starting position sign, right? And we sub in this, we are actually only finding the time taken for the particle to travel from equilibrium immediately in the next section to the desired displacement that we're looking for. What happens is Q is not here, Q is here. So it's like the time taken must be for Q to go down and then up again, then the displacement is here. We're trying to find the second solution of the trigo. Correct? Okay, but unfortunately you found t over 12, right? Let's say you had done that, right? Can we use that here? I think we can, right? I think we can. So this is your t over 12, like this period of time. Like from here, right, to here, this is t over 12. Okay, which because sine is symmetrical, which is the same as from here to here, this is also t over 12. All right, you understand what I'm saying? So if we understand it to be symmetrical, let me get rid of it. Right, let me get rid of it. Right, at the end of the day, we are trying to find, right, we're trying to find from here to here, like what's the time here to here? Half t minus t over 12. That's right. Then that will be the time difference between P and Q. Then you can take that divided by period. Then that's your, and then multiply by 2 pi. That will be your phase difference. Can? Okay. Ayyo. Okay, I do more. Hang on. I need to go off soon, so I'll try to rush through the last few. Okay. What is this? Oh, okay. Protons, electrons, charged particles, weight is negligible. And even if you do add in the weight into the calculations, it actually will be so small that whatever electric force that you calculate here will confirm be much bigger than the weight one. Then the number wouldn't even matter at all, even if you included the weight into the calculations. Okay, that one you listen. Okay, so I got okay. So I'll give you a blanket statement, okay? Electrons, protons, neutrons, always ignore the weight because it will eventually be negligible anyway. Look at the electrons mass. 9.11 times 10 to the power minus 31. Minus 31. That is 0.00000031 times 911. Right? So even if you do add in the force, the weight into the calculations, even if you do, you're basically almost the same as minusing 0. So Fe equals to Ma anyway. Okay? Alright. So then the question is, when do you then have to consider the weight? I'll tell you this, actually we always consider the weight. It's just that for the calculations for electron, it's so small that it would just end up being 0. So like the default statement is, right, the default statement is always consider the weight anyway, but you know, if you do, you'll be wasting a bit of time calculating this out. So for electrons, neutrons, protons, you can just skip the weight. Okay? So under what kind of questions when then the weight becomes not negligible, right? Okay? That's when you have oil droplets. When you see the phrase called oil droplets. When it's oil droplets, we're talking about entire physical, I can see this drop of oil kind of size. When it's oil droplet, you have to consider the weight, you have to consider the electric force. Because now the weight is not negligible. Then if this thing starts falling, for example, if it starts falling, for example, maybe because the electric force is now weaker, for example, right? Let's say it's a weaker electric force, okay? But then I say that, oh, it's falling with constant terminal velocity. Let's say it's, right, constant terminal velocity. The moment you hear terminal velocity, you have to consider the air resistance. So the air resistance, right, must be acting upwards so that the air resistance plus the electric force will equal to the mg. Then it will fall at terminal velocity, no resultant force. Okay, understand this now? Hang on, let me look at the next question. Okay. All right, what's your question for this one here? What? Can. Wait. Whatever. Without any further calculation. Okay, firstly, are these two charges the same type of charge? Are they both positive? Wait. No. No, one of them positive, one of them negative. Okay. One is positive, one is negative, right? Then they ask you, describe the variation of acceleration and speed. Okay. So E field strength tells us how strong the E field is. Wait, hang on. What are you putting in the middle? I think it's a positive test charge, is it? Is it a small little positive charge? Confirm, Is it electron? Then where is it going? It, if I put, it, part C, I don't have part C. No, I don't understand, because if I go and put electron here, right, it will just be attracted by the positive charge, right? Like it will just, wouldn't it be absorbed by the positive charge? Like, I sorry, what's the scenario? Did they just put an electron here, or did they do something to the electron, or what? Wait, hang on. Wait. Then how sure are you that A is positive and B is negative? It could be the other way around, what, right? But if the electric field is positive and I define pointing to the left as positive, then this one could be negative positive. What? Sorry, I don't quite understand. Again, this is what? This is your own school's question, is it? Or is it an actual paper? Yeah, it's not very well written. No, but okay, I get that. Hang on, let me think first. E field strength going down and up, right? But positive and remain positive. So it's either plus or minus. Okay, wait. Well, I mean, I'll just go through two scenarios. So let's say this is plus and this is minus, and then there's a negative charge that's being emitted. That means it was given a certain speed. That means because I didn't know it was given a certain speed, I thought it was just sitting there doing nothing at first. Right? So it's like a negative charge that was given an original speed, is it? Okay, so is it if it's flying towards the negative charge and it's flying away from the positive charge, I mean what will happen to the electron in general? No. Wait, why would it accelerate? It would decelerate. It would decelerate, right? Because if you tell me it will be a slower acceleration means that it will gain speed. No. I'm very confused by this. I don't get it at all. Like I'm looking at the answer key that you're seeing now. It says acceleration will decrease. So yeah, I don't get it. So what's happening is is this plus and this is minus, or is this minus and then this one plus? And does it have original speed in the first place? Can you send me the pictures of the other parts? Based on the answers that I'm looking at, yeah, it's a plus and minus. Okay, it's a plus and minus. So let me just redraw the whole thing for you. Hang on. You have a positive charge, you have a negative charge, and you have a tiny little charge that is that's being emitted with a certain speed v here like this. Okay, right? The graph shows you the E field strength between the two. It shows you something like this. It's like that, then like that. Okay. So the idea here is that I'm pretty sure is the case where the electron will experience an acceleration pointing to the left, which means that it will decelerate. Okay? If you're given an initial speed, right, and the acceleration is pointing to the left, right, then it will decelerate. So we have to say it decelerates. Okay? So the magnitude of deceleration is very big at first, but then the amount of deceleration it experiences gets the least here. So but it's still decelerating. So which means that once the particle reaches around somewhere here, for example, the speed is now lesser and the deceleration is also now lesser like this, right? It's like that. Okay. Then as it continues on towards the right side, okay, the speed will become like almost negligible, like this. Do you see that one? The smaller arrow there, right? But then the acceleration will again start to increase a bit more. Okay, right? This is like the three parts here. So since I mean based on the idea is that the okay, the question itself is not very clear. I can't understand the question itself. But when I saw the answer that you have copied down from the answer key, I sort of have an idea of what the teacher is asking. So the teacher is saying that this side plus, this side minus, right? I think your teacher used the words very loosely, and he said that the acceleration is, he said that the acceleration towards A will decrease, which is very annoying because you're not talking about the acceleration, you're talking about deceleration. The deceleration will decrease because you see the second sentence, speed will decrease from 0 to 6. That means what he's saying that this word here at the start here, that shouldn't be acceleration, it should be deceleration. Yeah. Okay. So according to the description I have, according based on what I see there, is that the particle will start to decelerate. So it moves to the right, but it accelerates to the left because of the electric force. The electric force for this electron is pointing towards the left side. So it will decelerate, it will cause it to become slower. But the magnitude of how fast is or how much is slowing down by, how much deceleration it experiences is getting less. Because somewhere around this region, the E field is not so strong. Okay? But it's still pointing backwards. And therefore the velocity is still decreasing. So this particle will continue to fly over here, right, up to the point where it's very close to the right side charge. The velocity is now very little. I don't know how much is it left. Maybe there's nothing left. Maybe there's some left. I don't know. But then the acceleration, the deceleration, sorry, the deceleration will become more again, right? Because it goes from high to low to slightly high again. So this is high deceleration, low deceleration, and then moderately high deceleration again. You understand this now? Anna? Okay, good. No, because that's what the question says. The question says that an electron is emitted from A and travels along AB. So we just take it as that, like somehow there's an electron that came out from the positive charge, oh. Yeah. The only possible way that this can happen according to real life context would be a radioactive particle that's emitting a beta minus particle. Right? So you imagine okay. Sorry, yeah, let me just let's say a radioactive nucleus. Okay? And a radioactive nucleus is positively charged. Right? Because it's a nucleus, the protons are inside, right? But during beta minus decay, right, one of the neutrons inside will become a proton, and in doing so, it will shoot out a beta minus particle. Okay? And a beta minus particle is negatively charged. So as it's being shot out, it's actually being attracted backwards by the nucleus again. You know? Yeah. So that's the idea lah. I guess that's the only way I can tell you like how can this be a thing, right? How can this be asked, right? That's the only thing I can think of. Sorry. Okay, yeah. Right. Then wait, now one more. Binary star, is it? Binary star. Okay. Can I show you the video for the binary star? I'm not too sure why your diagram is drawn like that though. Okay, but okay, no, sorry. Okay, what's your question actually again? Wait where is Newton's second law? Huh? Oh, in the next picture, is it? No. I was a bit confused. Wait which one, which one? Wait, sorry, this thing is a bit too big already. What, where? I'm so sorry, what are we trying to find? Angular velocity, yeah. Oh, okay. Uh, so that statement is useless one. Yeah, that statement is useless. I don't know why they included that statement. Like, it's no point on. Basically, binary stars is what? What is binary star? It's two stars orbiting around each other, right? Right. So there's a star orbit like that, then there's another star orbit like this. I mean they orbit in the same direction, by the way. So they orbit in the same direction like that. Correct? I mean, they are orbiting means what? Means got centripetal force, right? Then where are they getting the force from? What is that forces acting towards each other? What's that force called? Yeah, lor. So both of them, both sides, exert gravitational force on each other like this. Like F on A by B, F on B by A. Correct? Newton's third law tells us that these two forces are the same because gravitational force, right? Gravitational force on each other is the same. You don't actually have to code that. Like there's I mean it's quite dull. You don't even need to quote Newton's third law. In fact, you can even quote Newton's law of gravitation. The force on both objects are acting on each other, right? So like Newton's third law is just saying that the force that this guy acts on this guy is the same force that this guy acts on that guy. Same amount of force. That's Newton's third law. You don't even need to quote that. Like, yeah. Then the next thing is, so if there's a gravitational force acting on each other, then what do they do with the force? What do they use the force for? So Fg equals Fc, Gmm over d squared equals to mr mx omega squared, right? Or I think maybe this is a big M here because the x is the small x, right? Yeah, mx omega. That's it. Like you don't even need to quote second law. Like the fact that we know that the gravitational force is used to provide for a centripetal force, Fg equals Fc. I write down this equation. That's it, really. You don't have to quote the laws. You never have to quote the laws unnecessarily until they ask you in the question. Explain why. Using Newton's second law, using Newton's first law or third law, explain why, explain why, explain why. Then that one you have to look at the video. So for binary star system, right? For binary star system, if the two masses are the same, then they orbit they orbit in this sort of pattern. Like, let me draw it for you. So same mass like that, they will orbit like this. Like one guy will go this way, one guy will go that way. If they are of different masses, if one mass is slightly bigger than the other, right? Slightly bigger than the other, the big one will orbit a small radius, the small one will orbit a big radius. Okay? But the center of orbit is right here, and the distances to the center is different. Like, you know, this guy will be like, this one here will be x, and like if the distance here is like d, then the distance here is d minus x. Correct? Yeah. So big M is the one that has a shorter distance. Small m is the one with the bigger radius. But to understand that, you have to watch the video. So let me search for binary star. Hang on. I've been sending it out recently to other streams. Yeah, send it out. Okay? Anything else, guys? Yes, but the motion is always a tangent to the curve if it's traveling in a curve. So if you have so if you have an object that's like, you know, doing a curve like this, okay, and then I ask you, so what's the air resistance acting here? Like, ask you to draw an arrow of the air resistance acting here, right? So drag, right? Then you have to draw it as a tangent to the point here, like that. Then this is the drag force. Yeah, because the velocity of the object is going to be directly opposite it, like this. This is like the velocity. But that would mean that the drag has two components. One is a backwards component, one is a downwards component. Yeah. Yep. Last one. I only saw the binary star photo there. After the binary star. Oh, after the initial photos of binary star. Hang on. Okay, sorry. This one is it? Okay. Uh, is the new planet a bit bigger or a bit smaller? Uh-huh. And a lower density, right? So do you understand that planet P is like a small planet while Earth is a big planet? Do you understand that that would mean that Earth's gravity is actually stronger? So if you were to project something with a certain amount of KE on both planets, right, I would expect Earth's the object will only reach a certain height and then drop down, reach a certain height and then drop down. Whereas for planet P, it will fly an even greater height before it comes back down. Is that what you're having trouble to understand? Why would it be higher? Okay. Does me saying that it's a less gravity, does it help? Like, because it has lesser gravity, so it will, you can, like the idea is that if you go to the moon and you throw an object with the same effort that you do on Earth, do you understand that the object will fly higher? Yeah. Like, I mean, I think the idea here is, do you understand the intuition here first? Like, do you understand the kind of like the gut feel? Like it's higher lah, right? You tell me it's smaller, you tell me it's less dense. If it sounds like a lighter planet, it sounds like the gravity is not so strong. I would expect the object to fly higher, right? Because this KE, who gave the object the KE? Like it's projected, right? It's projected, right? Like what can you project it with? Okay, a launcher lah, right? Or maybe even a catapult. Okay? Like when I say that the KE is the same KE, like on different planets, would it be different or would it be the same? The same, right? Yeah, lah, exactly the same. Why? Because it's half mv squared, right? Half mv squared, half mv squared, right? So I think I guess the idea here is that, like, if the mass of the object is the same and the initial velocity of the object is the same, because they say that they are launched with the same speed, right? Right. Then I would expect them to have the same KE, right? So if they have the same KE, then I mean, likewise, I would still expect it to reach higher on a less strong gravity planet. The what? Sorry, one more time. Which is zero. Which is zero. Are you saying the KE at the maximum points there and there? Yeah, right? Why would you say the KE at the maximum points? I mean, yeah, lah, they basically KE is zero at their respective maximum point. Lah. You know why? Is it zero? Oh, no, 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 no. You're throwing in all the wrong words. It's not going to infinity, it's turning around. Yeah. So when things turn around and come back down, it will, yeah. Did you have that idea that it was going to go to infinity? Did you think that it was going to fly to infinity? No, it's going to turn around. Like when we ask you for maximum height, when we ask you for maximum height, it literally means at which point will you turn around, right? Because that's what maximum height means. Maximum height means that you manage to get to somewhere, but then that's like the highest you can go. And if that's the highest you can go, you can't go any higher, so it will fall back down. Okay? So I also do suspect that you have an idea that thinking that when you throw something up, you expect it to leave space. Yeah, but no. I mean, if you literally take a ball and I throw it up, it doesn't leave space. It comes back down to my hand, right? So that's what they are saying here. Okay. Let me ask you something, okay? Because of your this misconception, I can come back to this question, no problem. Anyway, you see the working also you are, so I think you also can understand. Let me ask you this, okay? All right. This is the other thing that I wanted to ask. Okay. This is planet Earth. This is a satellite. Okay. What is the satellite doing? Orbiting, so it's orbiting around the Earth, right? Okay. Right. Something happens to it. Something, you know, something here causes it to lose energy. Right? What will happen to the satellite? Satellite loses energy. What will happen to the satellite? No, as in like what happens to it? Where does it go? Does it fly away, or does it crash to Earth? That's where the mistake is. Because that's where I suspected you got the wrong idea already. Basically, okay, so you got to always remember, okay, you want to fly away, right? You want to go away, right? You must have even more energy than now. When you try to escape the Earth's gravity, always remember the Earth is always trying to suck everything in. Like everything that's around it, right, is always trying to pull everything in. So if your satellite loses energy, right, the next thing is going to happen is going to start falling towards Earth. It will start falling towards Earth. Whether or not it crashes or it goes to a lower orbit, it basically doesn't go further. Always remember that when you want to try to go further away, right? If you want to go further away from the planet, when you want to go like far away from planet, you need more energy. If you don't have the energy, you cannot go any further. You'll be stuck in the gravitational field. So it's a very common mistake that students make whenever I ask them, oh, what happens when it loses energy? Then the students will start thinking that, oh, you lose energy, then you drift off into space. Oh. That's absolutely wrong. It doesn't do that. Because because the idea here is that in order for it to go drift off into space, right, it needs a lot more energy. You cannot make the satellite lose energy and make it fly off. It's contradictory to each other. So yeah, but question is, does it even have enough energy to go to infinity or not? You need extra energy. Like whatever energy it has now, you need to give it extra energy. Right now, right, his energy here is only enough for him to orbit. If he lose energy, he will drop to a lower orbit. Right now he's only at this thing here. Like, if you want him to leave from this black color orbit to infinity, right, you need to give him extra energy. Then he can go. It's like you need money to go somewhere. If you don't have money, you will stick here. If you lose money, you will fall even closer. Only with money, then you can go somewhere further away. Can Okay, good. Hang on. Back to this one. So for both the planet P and Earth, I give them both the same amount of money, right? But Earth's gravity is very strong. So the amount, like the height that this object can travel up to is only this amount only. In fact, they say it's only 1.5 meters, right? So it's only 1.5 meters. But on a weaker gravity planet, right, with the same amount of money, you can go further up, right? You can go further up. But I don't think I don't think it is more than the escape KE. So it probably will not escape to infinity. There's a chance, I don't know, maybe, right? There's a chance for it to go to infinity. Maybe I threw this ball so hard on Earth, right, that for the same amount of KE, right, the KE could be greater than the escape KE. I don't know until I check the values. But what I do know is that the height will be greater than whatever we can get on Earth because the gravity of P sounds like it's lesser. Okay, then now the thing is this. Now we have to figure out how do we know how high it goes up? Like what's the method of finding here? Okay, so you got to check. Basically, this question is really frustrating because you need to check the GPE here. You need to check the GPE here. You need to check the GPE here. And you need to check the GPE there. A, B, C, D. All right, I just give it some letters first. GPE D minus GPE C equals to KE. GPE B minus GPE A equals to KE. Same KE ma, right? But then you have to expand it. So once you expand it, okay, once you expand it, it will be G M P M over R plus H minus negative G M P M over R equals to KE. Do you know why I put R plus H? Yeah, that's right. Okay, good. Then that's I mean, everything must always be calculated towards the center of the planet, right? Okay, and then, hang on, let me just try to find some more space here. Oh gosh, hang on. Right, then for the other one, negative GM Earth M over R plus 1.5, this is Earth, minus GM Earth M over R of Earth equals to KE. Do you see the working? Do you see that I put the, sorry, this is R Earth, so actually this one is RP, forgot. This one is the radius of P, like that. Yeah, no square also. Yeah, no square also. Yeah. So this question is really frustrating because the teacher is obviously, I mean, it's a tutorial question, so they're trying to challenge your calculations and all that. This is not really an exam style kind of question, right? Because you still have to go through the process of trying to find a mass of P and a mass of Earth, which you can find because they give you radius, right? And they give you density, right? So with radius, you can find volume, volume times density, you can find the mass. Furthermore, frustratingly enough, they don't even give you the density in kg per meter cube. They give it to you in gram per cm cube. So you still have to go and convert this 3,900 kg per meter cube. And this one is 5,500 kg per meter cube. Okay? Then at the end of everything, after you sub in everything all subbed in already, right? The small m also can cancel off already, yeah? I think so. Small m can cancel off. Basically, left hand side, this 2 is equals to right hand side, this 2. And then the small m can cancel off. That means I don't even need to care about the mass of the object. Everything all in, there's only one unknown left, which is h. Then you solve for h. That's the answer here. Okay? One of the next common mistake that students make, right? Next common mistake that students make is that they try to use SUVET. They try to use kinematics. But I guess you won't I guess you won't think of that. Okay, I'm not done yet. Wait, let me because I can now sense that you have difficulties in this one. This issue of this energy thing might be a very deep set issue. So maybe after the mid-year exams, maybe you have to focus a bit more on GPE and EPE questions. because those sound like a very, very deep set problem that you may have. Okay, but let me just try to do one example now. So, just in case like it comes out tomorrow, because this is an example that I know that quite a lot of teachers like to give. Okay, right. I want the rocket to escape. I want it to escape. Where is it supposed to go to escape? It needs to go to infinity. But if I want the rocket to orbit, do I give it the KE to escape? To orbit? But would it be the same amount of KE to escape? No, right? Because if I want it to orbit, I only want it to go to a certain distance. I don't need to give it the KE to escape, right? Okay, so let's say the KE to escape. Let's say the KE to escape for this rocket. Okay, right, for this rocket. Okay, for this rocket, just an example is 10 to the power 6 joules, right? 1 million joules. Okay, just imagine it's 1 million joules. Can? Okay, what if I give this rocket, right? So let's say the KE. Oh gosh. Okay. For this rocket, if I want it to escape, it's 1 million joules. Can? Okay, let me ask you this. What happens if I give this rocket 10 to the power of 5 joules? What will happen to the rocket? Wrong. The rocket will fly up and then crash back down. That's where you're getting wrong at. I'm not trying to make it orbit yet, right? If I want to make it orbit is another additional step. But if I simply just launch it like this, and I give it 10 to the power 5 joules, right? One common mistake is students think that, oh, you fly there, you'll just stay there. That's why you're thinking that it will orbit, because it will remain at this height. Wait, yeah, sure, that one, yes. But I'm trying to address the fact that some students think that, oh, if I give it energy, which is not the escape KE, it will fly and then stay here at this height. It will not stay there. It will crash back down because gravity will pull it. So if you want it to orbit, right, then yes, on top of this 10 to the power 5 joules, you need to launch it all the way there. Then yes, you need to turn it around so that it can have a tangential velocity. So then you have to include the orbital KE. That means you launch it already, then you need to turn it around and give it the orbital KE. Then it can orbit. Okay so far? Okay. Now, next question. Right, next question. So you now know that if you don't have enough energy, you will fall back down, right? Okay, now I'm gonna ask you this. What happens if you do give it 10 to the power 6 joules of energy? What will happen to it? You escape to, what will be his final KE? His final KE will be 0, right? Okay, hang on. Let me ask you this, okay? So am I right to say that the rocket will decelerate as it flies away? What? Will it decelerate as it flies away? Okay. I'm uncovering more and more problems now. What does decelerate mean? Yuhin, slows down. It slows down. Decelerate 的意思就是 slow down. So at the very start, I already gave it this amount of KE. That means I already one shot, bam, give it all the speed that it needs for it to be able to launch to infinity. So the KE at the start, the speed at the start is the highest. Then as it fly, look at the KE. The KE becomes what? You also told me zero, alright? Means that it stops. Very fast to stop means it decelerates. Okay, so yes, it decelerates. Okay, wait. Describe the deceleration. Is it a constant deceleration? Okay, all right, let me help you out here for the sake of time. It's a decreasing deceleration. Right? Why? So okay, wait, hang on. When we talk about deceleration, we need to talk about force. We use the KE to help us understand that it slows down. That's the relationship between KE and deceleration, but that's all. In order to determine why is it deceleration or like, decreasing deceleration, or how the deceleration is getting less and less, we need to consider the gravitational force. So what is the force like acting on the rocket when it's near Earth? The gravitational force is very strong, right? Okay, so the moment it starts launching off, right, in fact, at the very start, it experiences a very large deceleration because of this mg. The mg is pulling it back by a lot. But as it goes further and further away, right, the rocket goes further and further away, the mg gets less. So the amount of force causing it to decelerate is getting less. Therefore, it's called decreasing deceleration. Okay, right? The amount of deceleration is getting less. So as it flies off, right, eventually the mg is going to be very weak only, right? And then all the way at infinity, gravitational force is zero. Okay, Kenna, you understand this, right? So the rocket will fly to infinity with decreasing deceleration, eventually reaching infinity with a speed of zero. Okay, now I'm going to ask you a different question now. Okay, I'm going to give you 10 to the power of 7 joules. Ah, uh-huh. Uh-huh. How much? Your math also another kind. Can you take 10 to the power 7 minus 10 to the power 6? Actually, that's a lot of difference. Right? So it's 10 to the power 7 minus 10 to the power 6. It's a very big number. It's not 10, by the way. Yeah. All right. It's 999,000 or something like that now, okay? I just chose some random numbers, okay? Maybe I shouldn't have chosen that. Maybe I should have chosen like maybe 20 to the power 6 or something like that. But whatever it is, that means I'm giving more energy to this rocket than what it needs to escape the planet. So it will fly, but will it also experience decreasing deceleration? It will also, but it's just that it will reach infinity with a finite speed. Reach infinity with a finite speed. Yeah. Yes, I'm done. We will have more things to cover, right? We can't possibly cover everything, right, at one shot, right? So just I guess just continue practicing. But now I'm a bit worried because I didn't realize that you're so focused on your tutorials. I guess the tutorials, right? You have to fix it anyway, but they're not really exam style. So you gotta get used to the exam style kind of questions, especially for prelims. Can Okay, I gotta go. It's been quite long already, so I'm a bit shag. Yeah. If there's anything else, you can drop me some messages, but I'm not sure whether or not I'll be able to reply you everything by the end of today. I'll try lah. Okay. Okay, Hui Jin, you okay there? 睡着了。Okay, can. All right, see you guys.